Hello AP students, and welcome to the third and final installment of thermodynamics lessons for chapter 19. Please note, highlighted equations are the most important, and there's only a couple, maybe only one that's highlighted. Maybe I should go back and highlight. Anyway, I'll tell you which ones I should have highlighted and maybe forgot to do so. Okay, so let's just kind of review. When we pull values from Appendix C and calculate things like delta H or delta S or delta G using those tables, those are for standard conditions, okay? And in the previous lesson, there was a slide that told you what standard conditions meant. Things like all gases are at a partial pressure of 1 atmosphere. Anything that is aqueous is at a concentration of 1 molar, okay? However, and that works if we're talking about standard conditions, but most processes happen at non-standard conditions. And so there is a way to adjust delta G for this, and here is the equation, okay? At standard conditions, see, this 0 means standard. This is standard delta G. This would be non-standard delta G. It doesn't have the little 0 up above it. Okay? And this is R as in the gas law constant, R, T as in Kelvin temperature, and ln Q, and you remember what Q is from the last couple of chapters, right? Q is our reaction quotient. We set it up like K, but it's a test value, and it is not equal to K. Now, if we are at standard conditions, and everybody is at a molarity of 1 molar and a pressure of 1 atmosphere, then Q is guaranteed to equal 1. And natural log of Q is equal to 0. And this term of the equation drops out, and we are left with this. Okay? So at standard conditions, this term of the equation becomes irrelevant. The equation itself would be useful if we were at non-standard conditions. So let's talk about equilibrium. At equilibrium, a system is reacting in the forward and reverse directions at equal rates. That's essentially the same as saying it is not spontaneous forward or reverse because both processes are perfectly balancing one another. Okay? In that case, delta G is not positive, because that would mean it was non-spontaneous forward. Delta G is not negative, because that would mean it was spontaneous forward. Delta G is 0 at equilibrium. What that does is take this equation and convert it to this equation, which I can then rearrange to this equation, which is on your equation sheet, that relates standard delta G to the equilibrium constant for a system at equilibrium. The alternate form of that equation would be this. This is a math argument you'd have to look at. That'd be undoing, okay? Undoing a natural log is e to the something, okay? So it's the highlighted equation here that's on your equation sheet and that you are likely to use, okay? And this is not a 0. It wouldn't type it up top. Sorry about that. Wouldn't do it properly. So this equation is on your equation sheet, and this connects the free energy change, the spontaneity of a reaction, to the equilibrium constant for the reaction. Okay, so this is one way to apply this equation, and this is sample exercise 19.10. What I'd like you to do right now is just pause and read the given information here. Just read through it while you pause, and then I'll talk you through it. Give yourself a moment or two to process. So let's talk this through. We're talking about a boiling point of a liquid, and at the boiling point, temperature is not increasing or decreasing, and the liquid is in equilibrium with its gas. Okay? Now we're actually going to assume that we're at 298. We're estimating, rather than using an actual temperature. If we're at equilibrium, delta G equals 0. And if delta G equals delta H minus T delta S, that equals 0, which means this equation is true, which means this equation is true. Temperature of boiling is equal to the delta H divided by the delta S. Now this is an estimate because we are calculating delta H with a 0 and delta S with a 0 at 298 Kelvin. Okay? And these two values of delta H and delta S will change just a little bit if you're not at 298 Kelvin. So here's another equation. This one I'm not highlighting, it's not on your equation sheet. Okay, but it's a consequence of having a system at equilibrium. This is actually a more likely way that you would use the equation. So calculating the free energy change, which is delta G, not 0, because we're at non-standard conditions. Okay, so read this over. I want to calculate delta G for a mixture that contains some nitrogen, some hydrogen, and some ammonia. These are my initial concentrations: 1 atmosphere, 3 atmospheres, and 0.5 atmospheres. Okay? So going with the equation on the previous page, think about this for a moment. So to start this, because I am going to solve the equation for delta G, and that requires delta G 0, the standard delta G, the first thing I'm going to do is calculate delta G 0 using Appendix C. That would be to say delta G 0 equals the sum of the delta G's of formation for the products, which in this case is the ammonia, minus the sum of the delta G formation for the reactants. So here you can see that I have set up finding delta G using the information in Appendix C, pulled those values out of the delta G of formation column. Now I'm going to find Q for the equation on the previous page, that is products over reactants with exponents as needed. And so setting it up using the partial pressures that were given, we get a Q value of 108. And now I will solve the final equation. And here is the equation, and I will now plug in the values that I've calculated above. Take a peek and notice, if you would, that this value for R is not the standard value we would use in gas laws. In thermodynamics, we use this value of R. You can trust me that it would convert to the other if we converted work to joules, but both values are given on your equation sheet. So in thermodynamics, this is the value for R we use. And I have plugged this into RT ln, oops, I forgot the ln, hold on, hang on. All right, that's better. So I fixed that up. This is going to give me an answer in joules, and I'm going to want to divide this whole mess by 1,000 to make kilojoules. And so delta G will equal, get your calculator out and play with the math. I will do the same. And the value I'm getting for delta G at these non-standard conditions is negative 64.6 kilojoules. Notice that at standard conditions, it was already spontaneous, and at these non-standard conditions, it is in fact more spontaneous because it is more negative. So here are the two big takeaways. If delta G is very negative, that means the process is very spontaneous. If it's very spontaneous, it goes forward a lot and has a large equilibrium constant. If delta G is very positive, the system does not go forward. In fact, it shifts to the reverse a lot, and we have a very small K value. Those are the two biggest takeaways from this relationship between delta G and K. Here's one last question for you to ponder. We are talking about an insoluble salt. We don't know what the salt is. It doesn't matter to answer this question. Insoluble salt. This is KSP. We are asked to find what is delta G for the dissolving of the salt. Now you notice something. This is a pretty darn small K value. And so I'm expecting, I don't know, should I ask you what you're expecting? I'm expecting delta G to be non-favorable because this small K really favors the reactants by a lot. So I'm expecting a non-favorable delta G value. Okay, so use the equation on the previous page. Actually, is it on the previous page? It's not on the previous page. It's actually several pages back, and it's the highlighted equation. So solve the highlighted equation and see if you can deduce which of these answers is most likely, or is, in fact, not most likely, but is correct. If you are a little stuck, here's your equation. So pause and go ahead and solve. So I believe if you calculate this correctly and pay attention to the sign, you will get this, which is a very positive value, which means very unfavorable and very non-spontaneous, which should not surprise you for a very insoluble salt.